Greetings to all, and a warm welcome to our course focused on homogeneous catalysis. This educational program is tailored for those eager to establish a strong foundation in homogeneous catalysis and its contemporary applications in organic synthesis. As we progress through the upcoming modules, you will delve deep into the fundamental aspects of transition metal chemistry and catalysis. By the time you complete this course, you will be proficient in critically analyzing and effectively discussing the content of any modern research article within this field. To fully grasp the concepts presented in this course, it is assumed that you possess prior knowledge in general chemistry, inorganic chemistry, and organic chemistry. Our journey begins with the first module, where we will leverage your pre-existing knowledge to delve into the fundamental principles of organometallics and coordination chemistry. You will become acquainted with the primary categories of ligands present in transition metal complexes. We will also cover the 18-electron rule and strategies for valence electron counting in transition metals. Furthermore, we will examine the distinction between formal and actual oxidation states within transition metal complexes, as well as the interplay between coordination number and geometry. The module will wrap up with a discussion on how complexation with transition metals influences ligands. Organometallic chemists try to understand how organic molecules or groups interact with compounds of the inorganic elements, chiefly metals. These elements can be divided into the main group, consisting of the S and P blocks of the periodic table, and the transition elements of the D and F blocks. Main group organometallics, such as butyllithium and boronic acids, have proved so useful for organic synthesis that their leading characteristics are usually extensively covered in organic chemistry courses. Here, we look instead at the transition metals because their chemistry involves the intervention of D and F orbitals that bring into play reaction pathways not readily accessible elsewhere in the periodic table. While main group organometallics are typically stoichiometric reagents, many of their transition metal analogs are most effective when they act as catalysts. Indeed, the expanding range of applications of catalysis is a major reason for the continued rising interest in organometallics. As late as 1975, the majority of organic syntheses had no recourse to transition metals at any stage. In contrast, transition metals now very often appear, almost always as catalysts. Catalysis is also a central principle of green chemistry because it helps avoid the waste formation, for example, of magnesium salts from Grignard reactions that tends to accompany the use of stoichiometric reagents. This field thus occupies the borderland between organic and inorganic chemistry. Organometallic catalysts have a long industrial history in the production of organic compounds and polymers. In a catalytic application dating from the 1930s, D-cobalt octocarbonyl brings about hydroformylation, in which hydrogen and carbon monoxide add to an olefin to give a linear or branched aldehyde, depending on the conditions. A whole series of industrial processes has been developed based on transition metal catalysts. For example, there is intense activity today in the production of homochiral molecules, in which racemic reagents can be transformed into single pure enantiomers of the product by an asymmetric catalyst. This application is of most significance in the pharmaceutical industry where only one enantiomer of a drug is typically active but the other may even be harmful. Other examples include polymerization of alkenes to give polyethylene and polypropylene, hydrocyanation of butadiene for nylon manufacture, acetic acid production from methanol and carbon monoxide, and catalytic hydrosilylation to produce silicones and related materials. Beyond the multitude of applications to organic chemistry in industry and academia, organometallics are beginning to find applications elsewhere. For example, several of the organic light-emitting diode, OLED, materials recently introduced into cell phone displays rely on organometallic iridium compounds. Samsung has a plant that has been producing OLED screens since 2008 that uses cyclometylated iridium complex as the red emitter. Cyclometylated ruthenium complexes are used as photosensitizers for solar cells. Organometallic drugs are also on the horizon, with platinum complexes like cisplatin being used as effective chemotherapy medication to treat a number of cancers since 1978. Starting from 2001, the Nobel Prize in Chemistry has been awarded 5 times for groundbreaking contributions to homogeneous catalysis, primarily facilitated by organometallic chemistry. These awards specifically recognize achievements in asymmetric hydrogenation and oxidation reactions, olefin metathesis, cross-coupling reactions, organocatalysis, and, most recently, the development of click chemistry. These subjects constitute the central themes of our current educational curriculum. In organometallic compounds, nitrogen or oxygen donor coligands typical of coordination chemistry are very often present along with carbon donors. With the rise of such mixed ligand sets, the distinction between coordination and organometallic chemistry is becoming blurred, an added reason to look at the principles of coordination chemistry that also underlie the organometallic area. The fundamentals of metal-ligand bonding were first established for coordination compounds by the founder of the field, Alfred Werner. He was able to identify the octahedral geometric preference of hexacoordinated cobalt complexes without any of the standard spectroscopic or crystallographic techniques. In general, transition metal ions combine ligands to give a coordination compound, or complex. Together with being a subfield of organic chemistry, organometallic chemistry can thus also be seen as a subfield of coordination chemistry in which the complex contains a metal-carbon bond. Organometallic species tend to be more covalent, and the metal more reduced, than in classical coordination compounds. Typical ligands that usually bind to metal ions in their more reduced, low-valent forms are carbon monoxide, alkenes, and arenes. Central to our modern understanding of both coordination and organometallic compounds are d orbitals. Main group compounds either have a filled d level that is too stable or an empty d level that is too unstable to participate significantly in bonding. Partial filling of the d orbitals imparts the characteristic properties of the transition metals. Transition metal ions exhibit varying degrees of similarity to main group elements based on their electronic configurations. For instance, certain early transition metal ions like titanium-4, which lack d electrons, and late transition metal ions like zinc-2, with a full set of 10 d electrons, tend to behave more like main group elements. In classical Werner complexes, such as hexaamine cobalt-3 chloride, a relatively high valent metal ion binds to the lone pairs of electronegative donor atoms. In this case, the metal-ligand bond has a marked polar covalent character. The metal-ammonia bond consists of the 2 electrons present in lone pair of free ammonia, but now donated to the metal to form the complex. The most common type of complex, octahedral, adopts a geometry based on the Pythagorean octahedron. By occupying the 6 vertices of an octahedron, the ligands can establish appropriate metal-ligand bonding distances, while maximizing their ligand-ligand non-bonding distances. Alfred Werner developed the modern picture of coordination complexes in the 20 years that followed 1893, when, as a young scientist, he proposed that the well-known cobalt-ammonia complexes have an octahedral structure. In doing so, he opposed the standard view that the ligands were bound in chains with the metal at one end, as held by everyone else in the field. Back then, the availability of d orbitals for binding the ligand was not established, and naturally, he was opposed by supporters of the standard model, who only went so far as adjusting their model to consider new data. Jorgensen, who led the traditionalists against the Werner insurgency, was not willing to accept that a trivalent metal could form bonds to more than 3 groups, and so held to the chain theory. At first, as each new proof came from Werner, Jorgensen was able to point to problems or reinterpret the chain theory to fit the new facts. For example, coordination theory calls for 2 isomers of tetraamine dichlorocobalt-3 chloride complex. Up to that time, only a green one had ever been found, now called the trans isomer because the 2 chloride ligands occupy opposite vertices of the octahedron. According to Werner, a second cis isomer, then unknown, should have had the chloride ligands in adjacent vertices. He therefore needed to find this isomer. Changing the chloride to nitrite, Werner was indeed able to obtain both green, cis, and purple, trans, isomers of a similar complex shown here. Jorgensen quite reasonably, but wrongly, countered this finding by saying that the nitrite ligands in the 2 isomers were simply bound in a different way, via nitrogen in one case and oxygen in the other. Undismayed, Werner then found the green and purple isomers of the complex based on ethylene-diamine ligand, in a case where no linkage isomerism was possible. Werner even managed to separate the 2 enantiomers of the cis isomer of the complex based on ethylene-diamine ligand. This was quite astonishing, as at the time it was believed that only organic compounds could be optically active. These enantiomers demonstrate extraordinarily high specific rotation of 36,000 degrees, and it required 1,000 recrystallizations to resolve the rays mate. In 1907, Werner finally made the elusive purple cis isomer of tetraamine dichlorocobalt-3 chloride complex by an ingenious route starting from the necessarily cis cobalt complex based on a carbonate. Treatment of this complex with hydrochloric acid liberates carbon dioxide and gives the cis-dichloride complex of cobalt. Jorgensen, receiving a sample of this purple complex by mail, finally conceded defeat. In summary, we have explored the practical applications of organometallics and discussed Nobel Prize awards for advancements in homogeneous catalysis. You have also been introduced to Werner's coordination theory and essential organometallic definitions. In the upcoming lecture, we will delve into the primary categories of ligands found in transition metal complexes. Thank you for your dedicated attention. Hello, and a warm welcome to all as we resume our exploration of the introductory module on organometallics. Today's lecture will delve deeper into the fundamentals of metal-ligand bonding. We will also dedicate a significant portion of our time to exploring ligand classification, the various modes of ligand binding to metals, and intriguing concepts like hapticity. The transition series is formed by the systematic filling of the d shell, which in transition metals is of lower energy than the next s and p levels. Thus, transition metals have partially filled d orbitals and vacant s and p orbitals. In contrast, most of the ligands have filled sp hybrid orbitals and, for unsaturated organic ligands, vacant antibonding pi orbitals. Importantly, the d orbitals on the metal have similar symmetry and energy to the ligands' sp hybrid orbitals. Most ligands are Lewis bases and thus typically neutral or anionic, rarely cationic. Anionic ligands, often represented as X, form polar covalent metal-ligand bonds. Among neutral ligands, often denoted L, we find lone pair donors, such as carbon monoxide or phosphines, pi donors such as arans, and sigma donors such as hydrogen gas. Transition metals participate in two types of bonding, often simultaneously. Sigma bonds are formed by the overlap of filled sp hybrid orbitals on the ligand with vacant dsp hybrid orbitals on the metal. Ligands that are primarily lone pair donors, such as phosphines, amines, hydride, and carbanions, increase the electron density on the metal. These ligands fill one coordination site through one point of attachment and are called monohapto ligands, designated as eta1, which shows the number of adjacent ligand atoms directly bound to the metal. Unsaturated organic ligands, such as alkenes, alkynes, arans, carbon monoxide, and isonitriles, which have pi antibonding orbitals, bond somewhat differently. They, too, form sigma bonds by overlap of their filled pi bonding orbitals with the vacant dsp hybrid orbitals of the metal. In addition, filled d orbitals of the metal can overlap with the vacant pi antibonding orbital of the ligand, back-donating electron density from the metal to the ligand. It may seem paradoxical that an antibonding orbital can form a bond, but this orbital is only antibonding with respect to carbon atoms in the unsaturated organic ligand and can still be bonding with respect to the coordinating metal. In other words, unsaturated organic ligands can act as pi acceptors or pi acids, decreasing electron density on the metal. Because of these two modes of bonding, sigma donation and pi accepting or back bonding, metals can act as an electron sink for ligands, either supplying or accepting electron density. Therefore, the electron density on the metal, and hence its reactivity, can be modulated by varying the ligands around the metal. This offers a major method for fine-tuning the reactivity of organometallic reagents. Here you should remember that on the metal side, back bonding can only happen if the metal has electrons in the d orbitals. D0 ions, such as titanium-4 salts, cannot back bond and very seldom form stable complexes with strong pi acceptor ligands. There are two modes of pi back bonding and two types of pi acceptor ligands: longitudinal acceptors, such as carbon monoxide, isonitriles, and linear nitrosyls, and perpendicular acceptors, such as alkenes, alkynes, and arans. There is ample physical evidence for pi back bonding with good pi acceptor ligands. Carbon monoxide, which always acts as an acceptor, experiences a lengthening of the carbon-oxygen bond and a decrease in carbon-oxygen stretching frequency in the infrared spectrum upon complexation. This is a good indication of the population of a pi antibonding orbital on carbon monoxide, decreasing the carbon-oxygen bond order. The situation is a little more complex with alkenes. With electrophilic metals, such as palladium-2 or platinum-2, alkenes are primarily lone pair donors, and the carbon-carbon double bond length in such complexes is virtually the same as for the free alkene. With electron-rich metals, such as palladium-0, Substantial back bonding results. The alkene carbon-carbon bond is lengthened, and the hybridization at the alkaneate carbons changes towards sp3. The degree of pi back bonding has a serious effect on the reactivity of pi acceptor ligands, which will be described later. By back bonding, the metal can get rid of some of its excess electron density and delocalize it over the pi acid ligands. In tungsten hexacarbonyl, back bonding is so effective that the compound is air-stable and relatively unreactive. The carbon monoxide ligands have so stabilized the metal electrons that they have no tendency to be abstracted by an oxidant such as air. In hexatrimethylphosphine tungsten complex, in contrast, back bonding is negligible and the complex is reactive and air-sensitive. The d orbitals of transition metals are only fully available for back donation in low oxidation states. Although cobalt-3 does have a filled d orbitals, it is unavailable for back bonding. Cobalt-3 therefore cannot bind carbon monoxide. The high positive charge of cobalt-3 contracts all the orbitals with the result that the d orbital is low in energy and therefore cannot support back bonding. Ligands such as alkoxide and fluoride are pi donors because of the lone pairs that are left after one lone pair has formed the metal ligand sigma bond. Instead of stabilizing the d electrons of an octahedral ion as does a pi acceptor ligand, pi donor ligands now destabilize d electrons by what is effectively a repulsion between two filled orbitals. In sharp contrast, if the metal has empty d orbitals, as in the d0 ion titanium-4, pi donation from the pi donor ligand to the metal empty d orbitals now leads to stronger metal ligand bonding. D0 metals therefore form particularly strong bonds with pi donor ligands. For the sigma donor hydrogen gas, the metal ligand bond is formed via donation from the hydrogen-hydrogen sigma orbital to the metal d orbital. This interaction is accompanied by back donation from the filled d orbital of metal into the hydrogen-hydrogen sigma antibonding orbital as it is shown by arrows with numbering 4. Side-on bonding of sigma and pi donors results in short bonding distances to two adjacent ligand atoms. This type of bonding is represented as eta 2. For sigma donors such as hydrogen gas, forming the metal ligand sigma bond partially depletes the hydrogen-hydrogen sigma bond as electrons that were fully engaged in keeping the two hydrogen atoms together in free hydrogen gas are now also delocalized over the metal. Back bonding into the hydrogen-hydrogen sigma antibonding orbital causes additional weakening or even breaking of the hydrogen-hydrogen sigma bond. In case of strong back bonding, the hydrogen-hydrogen bond breaks and a dihydride is formed. This is the oxidative addition reaction, which will be described in detail in the following module. Formation of a sigma complex can be thought of as an incomplete oxidative addition, where only the addition part has occurred. This table classifies common ligands by the nature of the metal ligand bonds. Both lone pair and pi donors bind side-on to metals when they act as ligands. Hydrogen gas and alkane CH bonds behave similarly. Note that Lewis acids such as boron trifluoride and molecules like carbon dioxide can be ligands by only accepting an electron pair from the metal. In such a case, the ligand contributes nothing to the metal electron count. We saw that phosphines and carbon monoxide fill one coordination site through one point of attachment and are called monohapto ligands, designated as eta 1. The allyl group can act as a monohapto, 2-electron donor, or a trihapto, 4-electron donor ligand. In the latter case, two coordination sites are filled, and all three carbons are bonded to the metal, but the ligand as a whole is still a formal monoanion. The cyclopentadienyl ligand most commonly bonds in an eta 5 fashion, filling three coordination sites and acting as a 6-electron donor, although eta 3 and eta 1 coordinations are known. Now we should briefly discuss the relation between periodic trends and bonding in transition metal complexes. The orbital energies fall as we go from left to right in the transition series. For each step to the right, a proton is added to the nucleus, thus providing an extra positive charge that stabilizes all the orbitals. The earlier metals are more electropositive because it is easier to remove electrons from their less stable orbitals. The sensitivity of the orbitals to this change is as it is shown here. The s orbital, having a maximum electron density at the nucleus, is more stabilized by the added protons than are the p and d orbitals, with a planar node at the nucleus. The special property of the transition metals is that all three types of orbitals are in the valence shell with similar energies, so all contribute significantly to the bonding. Metal carbonyls, for example, are most stable for groups 4 to 8 because carbon monoxide requires back bonding to bind strongly, and in the later groups, the needed d orbitals become too stable to be effective. Organometallic compounds of the electropositive early metals have a higher polar covalent character than in the later metals and thus tend to be more air-sensitive, because they are more subjected both to oxidation by oxygen and hydrolysis by water. Finally, as we go down a given group in the D block from the first to the second row, the outer valence electrons become more shielded from the nucleus by the extra shell of electrons added. They are therefore more easily lost, making the heavier D block element more basic and more capable of attaining high oxidation states. Ligands may be hard or soft depending on their propensity for ionic or covalent bonding. Likewise, metals can also be hard or soft. The favored, well-matched combinations are a hard ligand with a hard metal and a soft ligand with a soft metal. Hard-soft combinations are disfavored because of the mismatch of bonding preferences. Early transition metals behave like hard Lewis acids and interact well with hard ligands, while metals from groups 8 to 11 are soft metals and interact well with soft ligands. This has many similarities with the hard-soft acid-base principles, and following a similar logic, one can say that ligands based on polarizable period 3 or higher p-block elements are soft. A good example of a soft ligand are phosphines. This table shows formation constants for different metal ion halide ligand combinations, where large positive numbers reflect strong bonding. The hardest halide is fluoride because it is small, difficult to polarize, and forms predominantly ionic bonds. It binds best to a hard cation. Iodide is the softest halide because it is large, easy to polarize, and forms predominantly covalent bonds. It binds best to a soft cation mercury 2, which is large and easy to polarize. In this context, high polarizability means that electrons from each partner readily engage in covalent bonding. Organometallic chemistry is dominated by soft-soft interactions as in metal-carbonyl, alkene, and arene complexes, while traditional coordination chemistry involves harder metals and ligands. Ligands that have a donor atom with more than one lone pair can often donate one pair to each of two or more metal ions to give polynuclear complexes, such as this ruthenium complex where L is a phosphine ligand. The bridging group is represented by the Greek letter mu. In particular, this dinuclear complex consists of two octahedra sharing a face containing 3 chloride bridges. Ligands with more than one donor atom, such as ethylene diamine, abbreviated as N, can donate both lone pairs to form a chelate ring. The most favorable ring size is 5, but 6-membered metallocycles are also often seen. Chelating ligands are much less easily displaced from a complex than are comparable monodentate ligands for the reason illustrated in this equation. When the reactants release 6 molecules of ammonia, the total number of particles increases from 4 to 7. This creates entropy and so favors the chelate. Equilibrium constants for complex formation are usually called formation constants. The higher the value of the formation constant, the more stable the complex. Chelate ligands can also be polydentate, as in these tridentate and hexadentate ligands. Tridentate ligands are also termed pincer ligands, a type attracting much recent attention. Ethylene diamine tetracetic acid, alternatively known as EDTA, can take up all 6 sites of an octahedron and thus completely wrap up many different metal ions. As a common food preservative, EDTA binds free metal ions so that they can no longer catalyze aerial oxidation of the foodstuff. Remember, reactivity in metal complexes usually requires the availability of open sites or at least label sites at the metal. Alternate types of electron pair are sometimes available for bonding. For example, aldehydes have both a carbon-oxygen pi bond and oxygen lone pairs. As pi bond donors, aldehydes bind side-on like ethylene, but as lone pair donors, they can alternatively bind end-on. Thiocyanate can bind via nitrogen in a linear fashion, or via sulfur, in which case the ligand is bent. In some cases, both forms are isolable. In the osmium-2 complex shown here, osmium is a very strong pi donor as osmium-2 is soft, and the L-type ligand on it is not a pi acceptor. The pi-basic osmium thus prefers to bind to the pi acceptor aromatic carbon-carbon double bonds of aniline, not to the nitrogen. Oxidation to osmium-3 causes a sharp fall-off in pi donor power because the extra positive charge stabilizes the d orbitals, and the osmium-3 complex slowly rearranges to the inbound aniline form. This illustrates how the electronic character of a metal can be altered by changing the ligand set and oxidation state. Soft osmium-2 binds to the soft carbon-carbon double bonds and hard osmium-3 binds to the hard amino group. Actor ligands associate, dissociate, or react in some way. They are particularly important in catalytic reactions when they bind to the metal and engage in reactions that lead to release of a product molecule. In hydrogenation, for example, hydrogen gas can associate to the catalyst that go through a cycle of reactions that leads to release of the hydrogenation product. Spectator ligands remain unchanged during chemical transformations but still play an important role by tuning the properties of the metal to enhance desired characteristics. For example, cyclopentadienyl fragment of this iron-based catalyst remains intact. It is a spectator ligand and imparts solubility, stabilize iron-2 intermediates, and influence the electronic and steric properties of the complex. It is an art to pick suitable spectator ligand sets to elicit desired properties. Apparently small changes in ligand can entirely change the chemistry. For example, triphenylphosphine is an exceptionally useful ligand, while the similar triphenylamine, triphenylbismuth, and trisphenophlorophenylphosphine are of very little use. The hard indonor triphenylamine is very different from triphenylphosphine. While the bismuth-phenyl bond is too easily cleaved for triphenylbismuth to be a reliable spectator, and the electron-withdrawing penafluorophenyl substituents of trisphenophlorophenylphosphine completely deactivate the phosphorus lone pair. Actor ligands may allow isolation of a stable material as a precursor to a reactive species only formed after departure of the actor, that species either being too reactive to isolate or not otherwise easily accessible. A classic example is chelating 1,5-cyclooctadiene that binds to rhodium-1 or iridium-1 hydrogenation catalysts. Under hydrogen gas, the cyclooctadiene is hydrogenated to free cyclooctane, liberating the active catalyst. Now let's consider platinum-2 complexes. These are 4-coordinate and adopt a square planar geometry, as it is shown here. Platinum-2 complexes can react with incoming ligands to replace an existing ligand in a substitution reaction, where a choice exists between two possible geometries of the product. As in these equations, the outcome is governed by so-called trans effect. For example, in the second step of the first equation, the ammonia does not replace the chloride trans to ammonia, but only the chloride trans to chloride. This observation means that chloride is a higher trans effect ligand than ammonia. In the second equation, once again, the ammonia trans to chloride is displaced, not the one trans to ammonia, which leads to the formation of the opposite isomer of cisplatin. Ligands that are more effective at labelizing a ligand trans to themselves have a higher trans effect. The effect is very marked for platinum-2 complexes, and the highest trans effect ligands either form strong sigma bonds, such as hydride and alkyl anions, or are strong pi acceptors, like carbon monoxide and olefins. Ligands based on polarizable period 3 or higher p-block elements, such as phosphines and molecules containing sulfur, also demonstrate a pronounced trans effect. High trans effect ligands also lengthen and weaken trans metal ligand bonds. This can be monitored in X-ray crystallography or in nuclear magnetic resonance spectroscopy by a decrease in the metal-ligand coupling. A trans effect series for a typical platinum-2 system is given here. The order can change somewhat for different metals and oxidation states. To summarize, in this lecture, you have gained insight into the fundamentals of ligand classification and the intricacies of metal-ligand bonding. We have explored the intriguing concept of backbonding and its impact on the stability of metal complexes. Our journey has also taken us through the distinct characteristics of pi donor and sigma donor ligands, shedding light on the metals that readily bound with them. Our discussion extended to ligand classification, considering hapticity, chelation capabilities, bridging potential, and their roles in catalysis. We have also scrutinized the hard-soft acid-base principles and their significance in coordination chemistry. Lastly, you have been introduced to ligands with a higher trans effect, facilitating substitution reactions within metal complexes. Our next lecture will delve into the 18-electron rule and valence electron counting in transition metal complexes. Thank you for your engagement. Hello everyone, and welcome back to the module focused on exploring the structure and bonding in organometallic compounds. In today's lecture, we will delve into the concept of the 18-electron rule and the methods of valence electron counting in transition metal complexes. Most of reactions presented in this lecture series proceed in the coordination sphere of a transition metal, and it is the precise electronic nature of the metal that determines the course and the outcome of these reactions. A very clear view of the nature of the metal is critical to an understanding of its reactivity. The main features of interest are the oxidation state of the metal, the number of d electrons on the metal in the oxidation state under consideration, the coordination number of the metal, and the availability of vacant coordination sites on the metal. The simple formalisms presented in this lecture permit the easy determination of each of these characteristics. Just as organic compounds follow the octet or 8-valence electron rule, typical organometallic compounds tend to follow the 18-electron rule. This is also known as the noble gas or effective atomic number rule because the metals in an 18-electron complex achieve the noble gas configuration. For example, in the Werner complexes, the cobalt has the same effective atomic number as krypton, meaning it has the same number of electrons as the rare gas. We first discussed the covalent electron counting model that is the most appropriate one for compounds with predominant covalency, such as most organometallics. To show how to count valence electrons by forming a compound from the neutral atomic components, we first apply the method to methane, where the simpler octet rule applies. An octet is appropriate for carbon, where 1 2s and 3 2p orbitals make up the valence shell. 8 electrons fill all 4 orbitals. The 18-electron rule, followed by many transition metal compounds, is justified on the ligand field model by the presence of 9 orbitals, 5 d orbitals, 3 p orbitals along with a single s orbital. A simple 18-electron case is shown in here on the instance of potassium nonhydridorenate. The net ionic charge of -2 needs to be considered along with the 9 hydride ligands. The 2 electrons added for the -2 charge came from forming the counterions. Note that X-type ligands in the covalent electron counting model are considered as 1-electron donors. Other anionic X-type ligands that also provide 1 electron to the metal on forming a covalent bond include methyl anion, chloride, etc. A neutral L-type ligand, such as ammonia, contributes its 2 lone pair electrons to the metal on binding as it is demonstrated for this Werner complex. The net +3 ionic charge requires subtracting 3 electrons from the count. These electrons are transferred to the anions, which are not shown here. This table shows how most first-row carbonyls follow the 18-electron rule. Each metal contributes the same number of electrons as its group number, and each carbon monoxide contributes 2 electrons from its lone pair. Back bonding makes no difference to the electron count for the metal. The free atom already had the pairs of d electrons destined for back bonding. In the complex, it still has them, now delocalized over metal and ligands. Where the metal starts with an odd number of electrons, we can never reach 18 just by adding 2 electron ligands, such as carbon monoxide. Each carbonyl complex resolves this problem in a different way. Vanadium hexacarbonyl is stable in spite of being 17-electron, but it is easily reduced to the 18-electron anion. The 17-electron reactive transient manganese pentacarbonyl is not isolable but instead dimerizes to the stable 18-electron dimer as a 5-coordinate monomer. There is more space available to make the metal-metal bond than in vanadium hexacarbonyl. This dimerization completes the noble gas configuration for each metal because the unpaired electron in each fragment is shared with the other in forming the metal-metal bond. Much as the 7-electron methyl radical dimerizes to give the 8-electron compound, ethane. In the 17-electron reactive fragment cobalt tetracarbonyl, dimerization also takes place to form a metal-metal bond, but a pair of carbon monoxide ligands also bridge. The electron count is unchanged whether the carbon monoxides are terminal or bridging because it is a 2-electron ligand to the cluster in either case. On the conventional model, a ketone-like bridging carbon monoxide gives 1 electron to each metal, so a metal-metal bond is still required to attain 18 electrons. The even electron metals can achieve 18 electrons without metal-metal bond formation, and in each case, they do so by binding the appropriate number of L-type ligands. An older counting convention based on the ionic model was developed early in the 20th century for classical Werner coordination compounds because of their more ionic bonding. The final count, deconfiguration, and oxidation state is always the same for any given complex on either model, only the counting method differs. People invoke one or other model without identification, so we must be able to deduce their choice from the context. Neutral L-type ligands pose no problem because they are always 2-electron donors on either model, but X-type ligands are treated differently. In the ionic model, each metal X bond is considered as arising from metal plus and X minus ions. To return to our organic example, whether we count octet and tetrachloromethane by the covalent model from the atoms or the ionic model from the ions, we get the same result. Applying the ionic model to the case of potassium nonhydridorenate gives a result similar to that seen in the covalent electron counting model. This table shows common ligands and their electron counts on both models. Neutral L-type ligands are always 2-electron ligands on either model, whether they are lone pair donors, such as carbon monoxide or phosphines, pi bond donors, such as ethylene, or sigma bond donors, such as hydrogen gas. Anionic X-type ligands, such as hydride, chloride, or methyl anion, are one-electron atoms or groups on the covalent model but two-electron ions on the ionic model. On the covalent model, a one-electron X radical bonds to a neutral metal atom. On the ionic model, a two-electron X anion bonds to a metal cation. Parkin and Green have developed a useful extension of this nomenclature by which more complicated ligands can be classified. For example, benzene can be considered as a combination of three alkene ligands, and therefore as three L-type ligands. Likewise, the eta-3-allo group is a combination of a carbon-carbon double bond and an alkyl anion, so it can be considered as mixed LX-type ligand. The electron count of a eta-3-allo, sometimes simply called a pi-allo, is 3 electrons on the covalent model and 4 electrons on the ionic model, as suggested by the LX label. The Greek letter kappa is normally used instead of eta when describing ligands that bind via non-contiguous atoms, such as a chelating kappa-2 acetate in this rhodium complex. As you can remember from the previous lecture, ligands that bridge are indicated by the prefix mu. For monoanions like chloride, thioalkoxide, or alkoxide and related cases, two separate 2-electron, 2-center metal ligand bonds can be formed, each involving a distinct pair of electrons. For these, we can write a structure such as in which the electron count for each metal is treated separately. For the metal on the left, we consider the bridging ligand as an X-type ligand, while for the metal on the right, the X-type ligand provides its lone pair as equivalent to a neutral 2-electron L-type donor. In this dimer of iridium, for example, each 14-electron Cp* ligated iridium reaches 18 electron by counting the bridging chlorides in this way and assigning the +1 ion charge to the right-hand iridium. For a ligand such as chloride with 4 lone pairs, bridging can also occur between 3 or even 4 metals leading to clusters. For a small class of ligands, such as bridging hydrogen, no lone pairs are present, and the bonding situation is different. Metal-hydrogen-metal bridge is best seen as involving a single 2-electron, 3-center bond that links all 3 centers with just 2 electrons. The classic case, diborane, although coming from the main group, embodies the same bonding pattern for each boron-hydrogen-boron bridge. Diborane can alternatively be considered as the double protonation product of the hypothetical ethylene analog, shown here, where the protons add to the 2 lobes of the hypothetical boron-boron pi bond. A hypothetical deprotonation strategy holds for transition metals. We can count any bridged hydride by removing each hydrogen as a proton, thus converting each metal-hydrogen metal to a metal-metal bond. Now we can count the resulting hypothetical structure. 14-electron Cp* iridium now reaches 18 electrons by counting 3 electrons for the hypothetical metal-metal triple bond and assigning -1 of the 2 anionic charge to each iridium. Here the bridging bonds, although shown as 2 separate bonds, are actually half-order bonds. Ligands such as bridging methyl and bridging carbon monoxide can be considered in a similar way. 0-electron neutral ligands are a growing class. For example, trisubstituted boranes, having 6-electron borons, complete their octet by accepting lone pairs from an L-type ligand. If the lone pair comes from an electron-rich metal, we have a metal-boron bond in which trisubstituted borane provides 0 electrons to the metal and thus leaves the metal electron count unaltered. The metal-boron bond can alternatively be written with formal charges as it is shown for these complexes of iridium. In this ligand substitution reaction, carbon monoxide leaves the complex easily due to the presence of a 0-electron ligand, which inhibits back bonding. The oxidation state of a metal is defined as the charge left on the metal atom after all ligands have been removed in their normal, closed shell, configuration, that is, with their electron pairs. The oxidation state is not a physical property of the metal, and it cannot be measured. It is a formalism that helps us count electrons, but no more. Typical examples are shown in here. The chemical properties of the ligands are not always consonant with the oxidation state formalism. In metal hydrides, for example, the hydride ligand is always formally considered to be H-, even though some transition metal hydrides are strong acids. Despite this, the formalism is still useful. Having assigned the oxidation state of the metal in a complex, the number of d electrons on the metal can easily be assessed by referring to the periodic table. This figure presents the transition elements along with their d electron count. At an oxidation state of 0, the number of d electrons is equal to the group number of the metal. If the metal has a formal oxidation state of 2, you can calculate the number of d electrons by subtracting the oxidation state from the group number of the metal. By referring to the periodic table, the d electron count for any transition metal in any oxidation state is easily found. The transition series is formed by the systematic filling of the d orbitals. Note that these electron configurations differ from those presented in most elementary texts in which the 4s level is presumed to be lower in energy than the 3d and is filled first. Although this is the case for the free atom in the elemental state, these two levels are quite close in energy. For the complexes discussed in this lecture series, we do not have free metal atoms. Instead, we have metals surrounded by ligands. This means that the assumption that the outer electrons are d electrons is a good approximation. The d electron count is critical to an understanding of transition metal organometallic chemistry because of the 18-electron rule, which states in mononuclear, diamagnetic complexes, the sum of the metal d electrons plus those contributed by the ligands never exceeds 18. The 18-electron rule determines the maximum allowable number of ligands for any transition metal in any oxidation state. Compounds having the maximum allowable number of ligands, that is, having 18 electrons in the bonding shell, are said to be coordinatively saturated, that is, there are no remaining coordination sites on the metal. Complexes not having the maximum number of ligands allowed by the 18-electron rule are said to be coordinatively unsaturated, that is, they have vacant coordination sites. Since vacant sites are usually required for catalytic processes, the degree of coordination is central to many of the reactions described in this course. With all the preceding information in hand, it is now possible to consider virtually any transition metal complex, assign the oxidation state of the metal, assess the total number of electrons in the bonding shell, and decide if that complex is coordinatively saturated or unsaturated. For example, the iron complex shown here is a stable, neutral species containing two formally mononegative ligands. One of them is the propyl group, an eta-1 2-electron donor X-type ligand. The other is the cyclopentadienyl ligand abbreviated as CP, which is an eta-5 6-electron donor ligand. The two remaining neutral carbon monoxide ligands contribute 2 electrons each. Since the overall complex is neutral and has two mononegative ligands, the iron must have a formal +2 charge, making it iron 2 with 6 d electrons. For an overall electron count, there are 6 electrons from the metal, a total of 4 from the two carbon monoxides, 2 electrons from the propyl group, and 6 electrons from the CP group, for a grand total of 18 electrons. Thus, here we have an iron 2, D6 coordinatively saturated complex. Ions of the same D configuration show important similarities independent of the identity of the element. This means that D6 cobalt 3 complex is closer in many properties to D6 iron 2 complex than to D7 cobalt 2. Here are shown other isoelectronic transition metal complexes, which demonstrate similar properties and catalytic activity. In general, the variable valency of the transition metals leads to many cases of isoconfigurational ions, and this idea helps us predict new complexes from the existence of isoconfigurational analogs. Some isolable complexes have an electron count other than 18. Most non-18 electron structures have less than 18 electrons. Representative examples are methyl titanium trichloride with 8 electrons, dimethyl niobium trichloride with 10 electrons, hexamethyl tungsten with 12 electrons, and bish-tridirt butyl phosphine palladium 0 with 14 electrons. Much rarer are D-block complexes with more than 18 electrons. Examples include cobaltocene with 19 electrons and nickelocene with 20 electrons. For the 18-electron rule to be useful, we need to know when it will be obeyed and when not. The rule works best for small, high-field, monodentate ligands, such as hydride and carbon monoxide. Such small ligands find no difficulty in binding as many times as needed to reach 18 electrons. An important class of late metal complexes prefers 16 electrons to 18 electrons because one of the 9 orbitals is very high-lying and usually empty. This can happen for the D8 metals of groups 8 to 11. Group 8 shows the least and group 11 the highest tendency to become 16 electron. When these metals have 16 d electrons, they normally adopt a square planar geometry, as in Wilkinson's catalyst, cisplatin, and related systems shown here. Although early transition metal complexes can have electron counts well below 18 electrons, an ambiguity often arises when the ligands have additional pi-type lone pairs that can, at least in principle, be donated into empty metal d orbitals. Remember our discussion about pi donor ligands. For example, hexamethoxytungsten is apparently a 12-electron species, but each oxygen has two pi-type lone pairs for a total of 24 additional electrons that could be donated to the metal. Almost any even electron count could therefore be assigned, and for this reason, electron counting is much less useful in discussions of early metal and D0 organometallic chemistry. Paramagnetic complexes generally do not obey the 18-electron rule, but many of these have reactions in which they attain an 18-electron configuration. For example, the 19-electron eta-5-cyclopentadienyl eta-6-phenyl iron 1 is a powerful 1-electron reductant, giving corresponding 18-electron iron 2 complex as product. Steric stabilization of otherwise reactive species is a standard strategy in organometallic chemistry. Steric bulk can permit formation of low electron count, low coordination number complexes, as in the isolable 14-electron bis-pi allyl complex of iron 2 shown here. In this case, the bulky trimethylsilyl groups enforce a syn-anticonformation that minimizes the steric clash between trimethylsilyl groups but blocks approach of additional ligands. The palladium complex presented here is an extremely useful catalyst for cross-coupling reactions. It is a relatively stable 14-electron complex, as the enhanced steric bulk caused by the 2-tritert-butyl phosphines limits the accessibility of palladium for other ligands. To sum it up, we have explored the 18-electron rule and delved into the covalent and ionic valence electron counting models. Our journey has encompassed understanding electron counts for common ligands and the determination of formal oxidation states of transition metals. This knowledge has empowered us to analyze electron counts and oxidation states within transition metal complexes. Furthermore, we have taken a closer look at the limitations of the 18-electron rule and the factors contributing to those limitations. As we wrap up this module, our final lecture will introduce the correlation between coordination numbers and geometry in transition metal complexes, along with insights into the effects of complexation. Thank you for your attention. Hello everyone, and welcome back to the introductory module on organometallics and homogeneous catalysis. In this lecture, we will explore the distinctions between the assigned formal oxidation state and the actual charge of the metal and transition metal complexes. We will delve into non-innocent ligands and their impact on altering the formal oxidation state of the metal in catalysis. Additionally, we will briefly address the effects of complexation and how the metal modulates the reactivity of coordinated ligands. Before we delve into the specific details about non-innocent ligands, it is worth recalling what we understand under the oxidation state of transition metal complexes. The oxidation state of a metal in a complex is simply the integer charge that the metal would have on the ionic model. For a neutral complex, this is the number of X-type ligands. For example, ferrocene has two L2X-type ligands, and so ferrocene is said to contain iron 2. For a complex ion, we need also to take account of the net charge. For example, in this positively charged ferrocene analog we have iron 3, and in negatively charged tungsten pentacarbonyl shown here the formal oxidation state of tungsten is -2. It is often useful to refer to the oxidation state and deconfiguration of a metal, but these only represent a formal classification and do not indicate either the real partial charge on the metal or even the trends in that charge as the ligands are changed. It is therefore important not to read too much into them. That is why ferrocene is considered as an iron 2 and not as an iron 2 plus compound. Iron 2 plus would only be appropriate for a predominantly ionic compound, such as hexaqua iron 2 sulfate. Similarly, tungsten hexahydride, in spite of being tungsten 6, is likely to be closer to tungsten hexacarbonyl than to tungsten trioxide in terms of the real charge on tungsten. In real terms, tungsten 6 hexahydride is probably more reduced and more electron-rich than tungsten hexacarbonyl, which is formally tungsten 0. Carbon monoxide groups are excellent pi acceptors, so the metal in tungsten hexacarbonyl has a much lower electron density than a free tungsten 0 atom. On the other hand, the tungsten-hydrogen bond in tungsten hexahydride is only weakly polar, and so the polyhydride has a much higher electron density than the tungsten 6 suggested by its oxidation state. For this reason, in organometallic chemistry the use of the term formal oxidation state is more appropriate. The maximum permitted oxidation state of a complex can never exceed the group number of the metal. Titanium can have no higher oxidation state than titanium 4, corresponding to minimum allowed deconfiguration of D0. If we now add an additional alkoxy group to this titanium-4 complex, it can no longer remain neutral and should be depicted as a -1 complex, as shown here. Likewise, there is also a minimum oxidation state corresponding to the maximum number of d electrons the metal can have, which is effectively 10 for the d shell. Platinum-0 complex bearing 3 phosphine ligands complies with the 18-electron rule, making it theoretically possible. However, a d12 platinum-2 complex would be prohibited. These limitations need to be borne in mind when proposing intermediates and reaction mechanisms. An increase in the positive ionic charge of a complex with this general formula decreases any backbonding to the ligands, all else being equal. It also makes the complex harder to oxidize but easier to reduce and changes the reactivity toward nucleophiles and electrophiles. For example, the carbonyl complexes shown here are isoelectronic, but only the negatively charged complex reacts readily with electrophilic proton, and only the cation reacts readily with the nucleophilic molecules like water, while neutral chromium hexacarbonyl does not react with any of these reagents. More problematic are cases in which even the formal oxidation state is ambiguous and cannot be specified. This problem affects any ligand that has several resonance forms that contribute to a comparable extent to the real structure but give different oxidation state assignments. This behavior makes the ligand non-innocent. For example, in one of the resonance forms of butadiene, it acts as an L2-type ligand, while there are resonance forms where butadiene behaves as an LX2-type ligand. The binding of butadiene as an L2-type ligand leaves the oxidation state of the metal unchanged, but when it functions as an LX2-type ligand, the oxidation state of the metal becomes more positive by 2 units. The oxidation state ambiguity can become severe. In the case of tris-butadiene molybdenum, we can attribute any even oxidation between molybdenum-0 and molybdenum-6 by counting the butadienes as LX2 or L2-type ligands. Fortunately, the electron count is unambiguous because it always remains the same for all resonance forms. To avoid misunderstanding, it is therefore necessary to specify the resonance form to which a formal oxidation state applies. For neutral ligands, such as butadiene, convention normally calls for the neutral form, L2-type ligand in this case. Yet structural studies on molybdenum show that butadiene often more closely resembles LX2-type ligand. In this tungsten complex, the S donor behaves as a dithione L2 ligand, making the metal D6 tungsten 0. Accordingly, the central carbon-carbon bond of the dithione is long, the carbon-sulfur bond is short, and the metal is octahedral. A small change in the substituents on the dithione leads to a different complex, where the metal has reduced the ligand by 2 electrons to give an enedithiolate. This is an X2 ligand, making the metal D4 tungsten 2. The ligand carbon-carbon bond is now short, the carbon-sulfur bond is long, and the metal geometry has converted to trigonal prismatic. Rather than the range of intermediate structures common for butadiene, we now see 2 sharply defined ligand types in different compounds, distinguishable from X-ray structural data. First-row metals typically have stable oxidation states 1 unit apart and undergo 1 electron redox changes as a result. The second and third row typically have stable oxidation states 2 units apart and prefer 2 electron redox changes. In catalysis, when organometallics have to bring about multi-electron reactions, 2 electron redox steps are desirable because they avoid high-energy, odd-electron intermediates. Although second and third row metals have been preferred up to now, the price rises of the precious metals and the green chemistry aspiration of avoiding rare elements means that first row substitutes will increasingly be sought. Redox-active, non-innocent ligands may help in this respect by providing an alternative source or sink of electrons in addition to the metal, thus potentially allowing multi-electron chemistry for the cheap first-row metals. Pincers and porphyrins are specially favored for redox activity because of the greater degree of multi-ring delocalization possible in these more extended ligand systems. Another non-innocent ligand class can gain or lose protons easily, in this case from the NH groups in the imidazole ring. Deprotonation alters the ligand class from L3 to LX2, which has a big influence on the properties of the complex. Chirek and his co-workers made significant advancements in applying this concept in catalysis involving the first-row metal complexes. Here one can see an example based on formal iron 2 catalyzed 2+2 cycloaddition reaction. The reaction commences with an X2L-type iron pincer complex, where the formal oxidation state of iron is 2. In the subsequent steps, a diene is coordinated to the iron complex, which is followed by the reductive coupling of the 2 olefin subunits. Notably, the formal oxidation state of iron appears to remain unchanged, while the pincer ligand undergoes oxidation to become an L3-type ligand. In the final step of the process, a reductive elimination occurs to yield the product, without causing reduction of the metal in the complex. Instead, the pincer ligand is reduced back to an X2L-type ligand. Now let's focus more on the effects of complexation. The chemical character of many ligands is profoundly modified on binding to the metal. For the full range of metal fragments in this general formula, there is a smooth gradation of metal properties from strongly sigma acceptor to strongly pi basic. Accordingly, in this complex, a typical unsaturated ligand, noted as Q, loses charge and becomes more electrophilic due to a sigma acceptor metal fragment. Conversely, the Q ligand gains electrons and, as a result, becomes more nucleophilic under the influence of a pi basic metal fragment. As an example, free benzene is very resistant to attack by nucleophiles, but reacts with electrophiles. In the benzene chromium tricarbonyl complex, in contrast, the chromium tricarbonyl fragment, as a good acceptor by virtue of its 3 carbon monoxide ligands, depletes the electron density on the aromatic ring. This makes the bound benzene susceptible to nucleophilic attack but resistant to electrophilic attack. Inversion of the typical reactivity pattern on binding is termed umpolung. If the metal in this generalized complex is in the middle range of electronic properties and is both a sigma acceptor and a pi donor, it might seem that the Q ligand would differ little from free Q in chemical character. In fact, the ligand can still be strongly activated by polarization. Sigma donation from the ligand to the metal usually depletes the electron density on the ligand donor atom, while pi back donation from the metal can raise the electron density on remote atoms in the Q ligand. A good example is molecular nitrogen, where the free ligand is nonpolar and notoriously unreactive. In the nitrogen complex, sigma donation to the metal comes from a lone pair on the nitrogen atom on the left. The back bonding from the metal goes into a pi antibonding orbital of molecular nitrogen. This means that the nitrogen atom on the left tends to become positively charged and the nitrogen atom on the right negatively charged on binding. This polarization enhances reactivity of the coordinated molecular nitrogen, facilitating protonation at the nitrogen atom on the right and nucleophilic attack at the nitrogen atom on the left. The effects of complexation are summarized in this table. If a ligand is normally reactive toward, say, nucleophiles, we can deactivate it by binding to a nucleophilic metal. The metal can then act as a protecting group. A ligand that is a note toward nucleophilic attack can be activated by binding to an electrophilic metal. Protection requires a stoichiometric amount of metal to be effective, and is no longer popular, while activation needs only a catalytic amount. Paradoxically, stronger metal-ligand binding does not always lead to stronger ligand activation. For example, hydrogen gas is most highly acidified on weak binding. The pK of hydrogen gas is near 35 when free, but often lies in the range from 0 to 20 for bound hydrogen, with the weakly bound ligands being most acidified. This is because the strength of metal-hydrogen binding largely depends on the degree of pi back donation, but stronger back donation reduces the positive charge on hydrogen that comes from the sigma donation from the ligand to metal. A knowledge of the behavior of free organic carbene, diene, or other species can be misleading in trying to understand their complexes. For example, dienes react with dienophiles in the Diels-Alder reaction, but diene complexes do not give this reaction. In a sense, the complex is already a Diels-Alder adduct, with the metal as the dienophile. The properties of both the metal ions and the ligands are profoundly altered upon complex formation. For example, cobalt-3 is very strongly oxidizing in simple salts, such as the acetate, which can even oxidize hydrocarbons. Werner's work showed that most of this oxidizing power can be quenched by binding 6 ammonias to the cobalt-3 ion. The presence of 6 strong sigma donor ligands in the resulting complex ion stabilizes the high oxidation state. Conversely, elemental molybdenum or iron is strongly reducing. However, molybdenum hexacarbonyl and iron pentacarbonyl are air-stable with only modest reducing properties, despite being based on iron 0 and molybdenum 0. This is because carbon monoxide removes electron density from the metal through back donation, thus strongly stabilizing the low oxidation state of the metal. A hard ligand tends to form ionic metal-ligand bonds, where the ligand retains more negative charge compared to soft ligands. This allows the metal ion to retain more of its positive charge, thus attracting additional hard ligands. Good examples are the hexahydrate ions of first-row D-block metals. In contrast, Binding soft ligands softens the metal, enabling it to bind other soft ligands, as seen in potassium ferrocyanide. This phenomenon is known as the symbiotic effect. The antisymbiotic effect, also referred to as transphobia, applies to pairs of soft ligands with a high trans effect on a soft metal. When a choice exists, there is a strong tendency for such ligands to avoid being trans to each other. High trans effect ligands tend to become cis and prefer to have low trans effect hard ligands as trans to themselves. These isomeric iridium complexes illustrate this point. The hard hydrides prefer to be cis to each other and have soft aqua ligands in the trans positions. Having water in the trans positions allows each hydride to monopolize covalent bonding along its own axis. To summarize, in this lecture, we have learned about the main distinctions between formal oxidation states and actual charges in transition metal complexes. You have been introduced to non-innocent ligands, which can undergo oxidation-reduction reactions or exhibit unusual electronic behavior when coordinating with a metal ion in a coordination complex. Finally, you have been acquainted with the effects of complexation and how the chemical properties and reactivity of different molecules can change upon complexation with a metal. In the final installment of this series of lectures, we will discuss the relationship between coordination number and geometry in transition metal complexes. Thank you for your attention. Greetings to all, and a warm welcome to the concluding lecture of the introductory module dedicated to the structure and bonding in organometallic compounds. Here, our primary focus will be on understanding the relationship between coordination numbers, deconfigurations, and the geometries of transition metal complexes. Before we delve into the examination of the relationship between coordination number and geometry in organometallics, it is helpful to review the definitions of oxidation state and deconfiguration for metals. The oxidation state of a metal in a complex is simply the integer charge that the metal would have on the ionic model. For a neutral complex, this is the number of X-type ligands. For example, ferrocene has two L2X-type ligands, and so ferrocene is said to contain iron 2. For a complex ion, we need also to take account of the net charge. For example, in this positively charged ferrocene analog we have iron 3, and in negatively charged tungsten pentacarbonyl shown here the formal oxidation state of tungsten is -2. The deconfiguration follows from the oxidation state and is the number of valence electrons that would be present in the free metal ion that corresponds to the oxidation state. In the positively charged ferrocene analog, for example, the oxidation state is 3, iron is in group 8, iron 0 has 8 electrons, and so iron 3 will have 5 electrons. The positively charged ferrocene analog is therefore a D5 iron 3 complex. Recall that any valence electrons are always assigned to the d orbitals only, not to d, s, and p, as in the configuration for the free atom. This table gives some leading characteristics of specific deconfigurations and shows how oxidation state and deconfiguration are linked. Most organometallic compounds occur in low or intermediate oxidation states, but high oxidation states are now gaining more attention. Back donation is severely reduced in high oxidation states because there are fewer non-bonding d electrons available. Additionally, the increased partial positive charge on the metal in a high oxidation state complex strongly stabilizes the d levels so that any electrons they contain become less available. Even deconfigurations are much more common than odd ones, particularly for the second and third row. Diamagnetic complexes are easier to study and so are more often reported. An exception exists for metal-metal bonded compounds, where odd electrons on each metal can pair up in the metal-metal bond. For example, you can recall D-manganese decacarbonyl mentioned earlier. Another good example is the recently reported D7 palladium-3 dimer complex, which demonstrates intriguing catalytic activity. The coordination number of a complex having only monodentate ligands is simply the number of ligands present. For instance, in potassium tetrachloroplatinate the coordination number is 4, while in tungsten hexacarbonyl the coordination number is 6. The coordination number cannot exceed 9 for the D block, because the metal only has 9 valence orbitals, and each ligand needs its own orbital. If the coordination number is less than 9, the unused orbitals will then either be metal lone pairs or engaged in backbonding. Many complexes can be discussed in terms of ideal geometries. Ignoring small distortions, each coordination number has one or more such associated geometries. We can predict the geometry of a given complex if we know the coordination number and deconfiguration of the metal in the complex by following the guidelines presented here. This table is constructed basing on the principle that the ligands in the complex attempt to stay as far from each other as possible, and each non-bonding pair of electrons occupies as much space as a metal-hydrogen bond. For instance, a complex with a coordination number of 4 and 8 electrons in the D shell of the metal will likely have a square planar geometry. These requirements are fulfilled for Wilkinson's catalyst, for which you should expect a square planar geometry. In a catalytic cycle, Wilkinson's catalyst can lose the chloride ligand by dissociation. This will lead to a 3-coordinated species still having 8 electrons in the D shell, but here you should expect a change in the geometry of the complex from square planar to a T-shaped structure. Coordination numbers lower than 4 are found with bulky ligands that cannot bind in greater numbers without prohibitive steric interference. For example, palladium-0 can coordinate only 2 tritert-butyl phosphine ligands, and related 3-coordinated complexes do not exist due to unbearable steric hindrance. The F-block metals do not have such electronic limitations and are, again, limited only by sterics, which means that coordination number values up to 15 are reasonable for them. It should be mentioned that the definition of coordination number and geometry is not clear-cut for multidentate organometallic ligands, as in ferrocene. Whether the molecule is 2-coordinate, 6-coordinate, or 10-coordinate is not that obvious. Indeed, there are 2 ligands, but 6 electron pairs are involved in metal-ligand bonding, and then carbon atoms are all within bonding distance of the metal. The definition most often seen involves counting the number of lone pairs provided by the ligands on the ionic model, making a coordination number of 6 for ferrocene, and we use it in what follows. To reach the maximum coordination number of 9, we need relatively compact ligands. The maximum attainable coordination number is also affected by the deconfiguration. A coordination number of 9 requires that the ligands have all 9 empty s, p, and d orbitals to occupy, so D0 configuration is needed. A good example of a 9-coordinated complex is potassium nonohydridorenate. 8 coordination requires D2 configuration or lower, and similar arguments apply to the other coordination numbers. To visualize the geometry of transition metal complexes, one can use the web-based application called Molecular Shape, developed by the University of Colorado Boulder. This visualization tool is based on the principle that the ligands in the given complex attempt to stay as far from each other as possible, and each non-bonding pair of electrons occupies as much space as a metal-hydrogen bond. Despite some drawbacks, this application can be extremely useful for visualizing the shapes of organometallic compounds in 3-dimensional space. Opening the application will present you with 2 windows, where you should select the window labeled Model. This will lead you to a user-friendly interactive interface displaying a linear structure of a complex with 2 ligands. Please note that in the top right corner of the window, you have the option to choose either a ligand that can bind to your metal via single, double, or triple bonds, or a lone pair of electrons. If we now click on the ligand symbol that can form a single bond with the metal, it will automatically add a ligand to the simplified model of the metal complex in the center of the screen. We want to start our examination with an octahedral complex, which means that we need to add 4 additional ligands to the starting linear model. We can remove one of the ligands by clicking on the X button in the top right corner. This will automatically transform the octahedral model into a trigonal bipyramidal complex, where the ligands maintain the optimal distance between each other. If we now add a lone pair of electrons to the trigonal bipyramidal complex, it will immediately transform into a square-based pyramid. This structure has a lot in common with the octahedral complex, with the main difference being that one of the ligands in the octahedral complex is now replaced with a lone pair of non-bonding electrons. Sequential removal of 2 ligands will turn the square-based pyramid into a pyramidal complex where we have 3 ligands and a non-bonding pair of electrons on the metal. Addition of the second pair of non-bonding electrons will transform the pyramidal complex into a T-shaped geometry, which is again driven by the tendency of the molecule to maintain a maximum distance between the ligands and non-bonding pairs of electrons. Eventually, if we try to add the fourth ligand to the T-shaped complex, the system will generate a square planar geometry, which is similar to the octahedral structure. Given that two of the ligands in the octahedral complex are now replaced with non-bonding lone pairs of electrons. Please remember that this web-based visualization tool is freely available to everyone, and you can utilize it to visualize the configurations of the complexes you will encounter in this course, as well as for the catalysts involved in your studies. As we saw in Werner's work, octahedral complexes tend to be very geometrically stable. Cis ligands stay cis and trans stay trans. The same holds for square planar complexes. Other common geometries tend to be more fluxional, with the ligands permuting their positions within the coordination sphere. For trigonal bipyramidal cases, for example, several isomers can coexist in rapid equilibrium. For instance, the trigonal bipyramidal complex of rhodium presented here has two such forms. In conclusion, we have learned about the relationship between coordination number, deconfiguration, and the geometry of transition metal complexes. We have observed that the geometry of organometallic compounds is influenced by the tendency of ligands and non-bonding lone pairs in the given complex to stay as far from each other as possible. You have been introduced to a web-based application that can be used to visualize and understand the geometry of transition metal complexes. Good luck with your midterm evaluation and the upcoming modules on the use of organometallics in organic synthesis. Your contributions to this module are greatly appreciated.